Okay, so I think we can start.
Okay.
Yeah, so let's welcome everyone. Today we have Suprajo Das, and he'll speak about epsilon multiplicity for graded algebras. Go ahead.
Sure. Thank you for the introduction. So the talk is called the epsilon multiplicity for graded algebras. So this is based on a part of my thesis and also some work which I did recently. Okay, so I guess the first thing to do would be to motivate the definition of epsilon multiplicity. So I guess we'll start with the more classical notion, which is that of the Hilbert-Samuel multiplicity, right? So we have a Noetherian local ring R, cruel dimension D, and I is an imprimary ideal in the ring. Then we know that for n large, this function, which associates to every positive integer n, the length of this Artinian ring, R mod I to the n, that behaves like a polynomial for large n of degree d. And this polynomial, it has got a name. It's called the Hilbert polynomial of I. Okay. All right. So with that in mind, we can define what's called the Hilbert-Samuel multiplicity. That's this length of R mod I to the n divided by n to the d, and you multiply by this normalizing factor d factorial. Okay, and then you take the limit. So in other words, this is the normalized leading coefficient of the Hilbert polynomial of I, right? Okay, and in fact, this is always going to be an integer. Okay. All right, so this is all basic stuff. And one use of Hilbert-Samuel multiplicity was given by David Rees. So he showed that the property of being integrally dependent can be captured by equality of Hilbert-Samuel multiplicities, right? So his theorem goes as follows. So if you have an equidimensional universally catenary Noetherian local ring, if you have a containment of imprimary ideals J and I, then these two statements are equivalent. That is, I is integral over the ideal J if and only if their Hilbert-Samuel multiplicities are the same. Okay, so the implication 1 implies 2, that works very generally. It's only the other implication 2 implies 1, which requires this additional structure on the ring R. Okay. All right, so what if we need to generalize this Hilbert-Samuel multiplicity? We see that it only works for imprimary ideals, right? What if we need a notion for arbitrary ideals? And one such solution is provided by the epsilon multiplicity of an ideal. So it's kind of the same setup. We have a Noetherian local ring R, cruel dimension D, but this time we pick any ideal in R. And then the epsilon multiplicity of I is defined as follows. So you can no longer talk about the length of R mod I to the n because it doesn't make sense for arbitrary ideals. What you can do is we can look at the zeroth local cohomology with respect to the maximal ideal of the ring R mod I to the n, right? So then it becomes an Artinian module, and you can talk about its length, okay? And then you divide by n to the d, multiply by the normalizing factor d factorial, and take the lim sup. So a very natural question to ask is, why is it a lim sup but not a limit? So it's simply because of the reason that we do not know whether it's going to exist as a limit or not. But lim sup, by definition, it's always guaranteed to exist, right? So, and one can see that if you replace I by an imprimary ideal, right, it just gives you the usual Hilbert-Samuel multiplicity of I, okay? And this was first defined by Ulrich and Validashi, okay? So what's the need for generalizing this invariant? Well, one motivation comes from their theorem. So they were able to give a generalization of the theorem of David Rees using epsilon multiplicity. So this is how the theorem goes. So R is a locally equidimensional, meaning if you localize R at any prime P, that's an equidimensional ring. Okay, so if you have a local equidimensional universally catenary Noetherian ring, and let J in I be any ideals, not just imprimary, okay? And also one has to assume that the smaller ideal is not contained in any minimal prime of R. Then these two statements are equivalent. That is, the bigger ideal is integral over the smaller one, if and only if the epsilon multiplicity of I and J at every prime P are the same, okay? So this gives a nice generalization of the statement of Rees, okay? It also has applications in what's called isolated singularities, okay, which we're not going to discuss here. Okay, so now some previously known results about epsilon multiplicity of ideal. So in the same paper where they introduced this new multiplicity, they also showed that this is finite. In other words, when you take the lim sum of that particular sequence, it doesn't blow up to infinity. Okay. Next is a statement about limits. So Katkowski, he found a theorem where you can actually replace the lim sum in the definition of epsilon multiplicity by a limit. So he shows that if you take an analytically unramified local ring, meaning the completion of the ring has no nilpotent, it's reduced. Okay, and if you take any ideal in that particular ring, then epsilon of I does exist as a limit. Okay. Right. And the third point, this shows one of the fundamental obstruction in working with epsilon multiplicity. So in Hilbert multiplicity, the function which is associated to the Hilbert multiplicity, that is this n going to length of r mod I to the n, that has polynomial-like behavior for large n, right? But we cannot expect that to hold for epsilon multiplicity. Okay, so in fact, there is an example by Katkowski, Ha, Srinivasan, and Theodorescu, where they show that this epsilon of I can in fact be an irrational number. Okay, so that dispels sort of all hope of expecting polynomial-like behavior, right? And in fact, in the example which they construct, they take the ring R to be a regular local ring of dimension 4 over complex numbers. So even for very nice rings, you cannot expect nice behavior from the epsilon multiplicity. Okay? But there are instances where this does turn out to be a rational number. For example, there's a theorem by Herzog, Puthin, Purakal, and Varma, where they show that if you take a monomial ideal in, okay, I should have been more careful. So here K represents a field. So if you take a polynomial ring over a field localized at its graded maximal ideal, in that case, epsilon of I will exist as limit and it will in fact be a rational number. Okay. So Esquivel, he generalized this result in his PhD dissertation. He showed that if this graded R algebra, I mean this one, okay, if that graded R algebra, which is the saturation of the Riesz algebra of I with respect to the maximal ideal, if that turns out to be Noetherian, then epsilon of I, it does exist as a limit and is in fact a rational number. In fact, what he shows is that in the above example, if you take R to be this polynomial ring localized at its homogeneous maximal ideal, take I and monomial ideal in that ring, then the highlighted algebra is in fact Noetherian. Okay, and in fact, his thesis provides a very systematic study of the development of epsilon multiplicity. It contains almost all the results which I have stated so far, along with its proof. So it's a very complete reference to this sort of thing. Okay. All right. So I guess Ulrich and Validashi, they in fact not only define epsilon multiplicity of an ideal, they defined what's called the relative epsilon multiplicity for graded algebras, a much more general notion. So we're going to define that, but before that, we need some preliminaries. So we fix a Noetherian local ring R. You have a graded R algebra T, meaning the 0th piece is R, and it's graded by natural numbers. That is, take the product of Ti, Tj, it's going to land inside Ti plus j. Okay. Then we need this notion of standard graded R algebra. So it's a graded R algebra which is generated by finitely many elements in degree 1. Okay. So as you would expect, this is going to be isomorphic to. So it's a quotient of a polynomial ring over R in some variables, and the polynomial is given the usual standard grading, that is a degree of each variable is 1, and then quotient it out by some homogeneous ideal in that polynomial ring. Okay. Slightly more general notion is that of a Noetherian graded R algebra. This is, well, this means that it's also finitely generated R algebra, but the generators, they live in finite degrees, not necessarily in degree 1, in which case you call it a standard algebra, right? And In fact, a Noetherian R algebra would be isomorphic to, well, this time you cannot expect a standard graded polynomial ring, but this time you expect a weighted polynomial ring, where the degree of each variable is some positive integer ai, and then you quotient it out by some homogeneous ideal in that polynomial ring. Okay, so that's a Noetherian graded R algebra. Okay, so once you have a Noetherian algebra, there's a very well-known result. Okay, so this is a reference to Bourbaki. So this shows that a Noetherian algebra, it's very closely related to that of a standard algebra. Okay, this is what the theorem is. The point is, this is how you can associate a standard algebra to T. So you define this algebra T prime, where the nth degree piece is TAN, which by the theorem above, right, by this result, it's TA raised to n. Just simply plug in R equals 0. Okay, and this is a standard algebra, and the point is, this gives us a lot of mileage in the sense that if you can prove something for standard algebra, it is sometimes possible to lift those results to Noetherian algebra using this kind of structure theorem. Okay, good. All right, so now we're ready to define what's called the relative epsilon multiplicity for graded algebras. So let A and B be two Noetherian graded R algebra, and the inclusion, it's a graded inclusion, that is A n is in Bn for all n. Then the relative epsilon multiplicity of A with respect to B is defined to be, well, it's the length of the zeroth local cohomology of the quotient Bn over An. Okay, then you divide by n to the dimension of B minus 1, multiply by this normalizing factor, dimension of B minus 1 factorial. Then again, you take the lim sum. Okay, but actually Ulrich and Balidashi, they define this notion not for Noetherian, but just for standard algebras. But we require this more general definition for the purposes of our talk. Okay, all right. So now let's get back to some known results about this multiplicity. So Ulrich and Balidashi, they showed that if you take A and B to be standard graded, then this relative epsilon multiplicity is going to be a finite quantity. Okay, and in fact, if you allow A and B to be Noetherian, but also assume that R is universally catenary, then we can show that this relative epsilon multiplicity is also finite. So this is where we make use of the structure theorem to lift the result in Noetherian algebra. But then we also have to use this dimension formula due to Nagata, right? And there the equality happens only when we assume R to be universally catenary, okay? Which is why we have this assumption in the more general case. Okay. Next statement, well, so Ulrich and Balidashi was able to generalize the statement of Ries to standard algebras. So what they showed is that if you have a graded inclusion of two standard algebras, then the bigger one is integral over the smaller one, if and only if they satisfy some equality condition on the relative epsilon multiplicity. Okay, so that gives a vast generalization of the theorem of Ries. Next is a statement about the existence of relative epsilon multiplicity as a limit. So this is essentially Katkowski's theorem. So he showed that if you take R to be an analytically unramified local ring, dimension D, okay, then we need to specify what B's and A's are. So B is taken to be a standard graded polynomial ring over R in some variables, and A is a standard graded R subalgebra of B. Okay, so in that setup, the epsilon multiplicity of A with respect to B does exist as a limit. Okay, so this is a very general statement, and in the remainder of the talk, our goal is to give a generalization of this particular theorem. So what we do is that we replace A and B by Noetherian algebra, not just standard graded, and we allow them to be any reduced Noetherian algebra, not necessarily polynomial rings. Okay, but we do pay a price for this generalization. We cannot assume R to be just analytically unramified. We have to assume that R is excellent and reduced. But although in practice, analytically unramified local rings are not too far from being excellent and reduced. Okay, and also if you look here, sorry. this portion, the d plus n, that is nothing but the dimension of B, because that's the dimension of R plus the number of variables that you attach to this polynomial ring, right? Okay. Okay, and this is what I have just said, that we extend this result. And this is our main result. That is, if you have an excellent local ring, if you have two Noetherian algebras, reduced Noetherian algebras A and B, being a graded inclusion, and also one is to assume this technical condition on these minimal primes. That is, the minimal primes of B, they do not contract to the maximal ideal of R. Okay, so in fact, this is a very mild condition, and this is almost always satisfied. In fact, this is satisfied when, let's say, R to B is a flat extension, but this also works in much more general setup. Okay, and one also has to assume that if A1 is contained in P, all the higher ANs are also contained in P. And in fact, this condition is also unavoidable, because one can obtain very silly counterexamples if one doesn't assume this particular condition. Okay, and then in this setup, epsilon of A with respect to B will exist as a limit. Okay. All right. So now our goal would be to give a proof of this theorem under more restrictive hypothesis. Of course, we cannot present a general proof because the proof is long and messy, but under more restricted setup, we can at least hope to give a proof in this talk, okay, or at least sketch a proof. Okay, so before we embark on the proof, we still need a couple of definitions. So first is this definition of a graded family of ideals. So let R be any ring. I is a sequence of ideal in R. We say it's a graded family if the zeroth ideal, that is the I naught, that is R, and the product of II and ij lands inside I plus j. So in other words, if you look at this direct sum, In, where n runs over all natural numbers, that forms a graded R algebra. Okay. And what's a Noetherian graded family? Well, as you would suspect, that it's a graded family, and this this associated algebra, right, direct sum In, that's a Noetherian algebra. Okay. Okay. Next, we come to a very fundamental theorem due to Swanson. Okay, and this is what a theorem reads, that if you take R to be a Noetherian ring, I to be any ideal in R, then you can find an integer c bigger than 0, such that for all n, all the higher powers of I will have this sort of primary decomposition, such that you have a linear growth here, right? So this statement, this containment is nothing but a statement about linear growth, right? And there's a very recent paper in arXiv, which came out recently due to Montano and Cedrois, and they showed that the Swanson's theorem, it can also be made to work for not just powers of a fixed ideal, it will work for a Noetherian graded family, okay? And by a minor modification of the proof, I really mean it's a one-line modification, okay? So there is really not much meat in that modification. Okay. Okay. Now we are going to sketch a proof of our main result, but under more assumptions. So we are going to assume that R is not just any excellent reduced ring, but rather it's very restrictive. It's a formal power series ring over an algebraically closed field K. Okay, and we're also going to assume that A and B are not just reduced algebras; they're also domains. Okay, so A and B is a containment of Noetherian graded R algebras, which are also domains. And also one has to assume that A1 is not 0, because otherwise you can obtain very easy counterexamples to this theorem. Okay, the reason we're assuming them to be domains because then we don't have to worry about those minimal prime conditions. Okay, and we will try to give a proof in this setup that epsilon of A with respect to B is going to exist as a limit. Okay, all right. So I guess the first step is a reduction argument. So here we will first reduce to B being standard. Okay, so this is how the argument goes. Now, since B is a priori Noetherian, we can write B as a quotient of a weighted polynomial ring, right? So we can assume B has this kind of structure. And since B is also reduced, I can assume that I is radical, right? In fact, I think we have assumed that they are domains. So I can assume that I is a homogeneous prime, right? Right. Okay. And now once you have this explicit description of B, I can embed it into an algebra C as follows, right? And in this case, just note that C is in fact a standard algebra. And this extension, it's an integral extension, right? So we have extended B by a standard algebra, which is a graded finite extension of B. And under this setup, one can show that the relative epsilon multiplicity won't change. Okay, of course, this requires a proof, but this can be done using ideas of Ulrich and Validashi. Okay, so the point is we can replace this B by this algebra C, right? Okay. Now, you consider this graded inclusion of these R algebras. Okay. Now A's and B's were as before, but then we introduced this algebra A prime, which is nothing but the saturation of A with respect to the maximal ideal of R. Now the point is, even if you assume A to be standard, you cannot expect this A prime to be even Noetherian. It can be very possible that this is a non-Noetherian algebra. Okay, and this is sort of the reason why this epsilon multiplicity doesn't have polynomial growth even for large n. Okay. All right. Now the point is we're going to apply somehow this more generalized Swanson's theorem, but for that we need a Noetherian graded family, right? Now, for every integer n, you can consider the extension of an in B that forms an ideal in B, and then you run it over all n, and that forms a Noetherian graded family simply because A is a Noetherian algebra, right? Now you apply Swanson's theorem, and from that theorem you have a C0, right? Such that those linear growth habits, right? And using that, one can show that one has this sort of identity. Now the point is, one-way inclusion is obvious, but it's the other way around which requires this powerful theorem of Swanson. Okay, so once you believe this statement, we can get a short exact sequence of R modules as follows. And if you look at the third term in this short exact sequence, that is nothing but the zeroth local cohomology of Bn over An, right? Now you can write that length as a difference of the middle guy and the first guy, right? And then you divide that equality by dimension of B minus 1 and hope to take limits, right? So now it suffices to prove, right, in view of this short exact sequence, that these limits exist, right? So our next theorem would be a theorem which will say that these limits will exist. Okay, good. So this is our theorem that if you have a Noetherian complete local ring, B is a reduced standard graded R algebra, and A is any graded R subalgebra of B. So here note that you cannot assume A to be even Noetherian, because eventually you're going to apply this theorem to these sort of algebras, right? But these can be very well be non-Noetherian, right? So we have to allow for that flexibility. All right, and also assume that A1 is non-zero, and if this lim sup, right, if you can find a P such that this lim sup is finite, then the statement is that it's going to exist as a limit. Okay, and in fact, one can show that in the above situation, if you replace this limit, right, by a lim sup, it's actually going to be finite. Of course, that requires a proof, but let's just assume that that works. Okay, so now our goal would be to give a proof of this particular theorem. And the proof is kind of interesting because we're going to cast this algebraic problem in a problem in convex geometry, okay, and then use methods of convex geometry to show that these limits will exist. Okay, And this uses those ideas of open curve bodies. Okay, and again, since we're working in this restricted setup, we're going to assume that R is a positive string over some algebraically closed field K. Okay, so the first step, well, the B there, so if you go back, right, so B was a reduced Noetherian, reduced standard graded R algebra. So we have a graded maximal ideal in B. So you localize B at that unique graded maximal ideal. And the point is to first construct a regular local ring having the same field of fractions as B, which is going to dominate B at this homogeneous maximal ideal, plus it satisfies other properties, okay? And this is how we're going to construct that particular regular local ring, okay? So what we do is, well, you look at this affine scheme. So you localize B at this homogeneous maximal ideal, look at the spec of that. Now that has got a unique closed point, right? So you blow up that unique closed point, okay? And now it may not be true that the blow up that you get is a normal scheme, right? So what you can do is take a normalization of that blow up, right? And you call that composite map pi and denote the normalization of the blow up by X, okay? Good. Then this morphism pi will have all these four properties. First off, this map pi is of finite type. Why is it so? It's because the first map is a blow-up. Now, blow-up is a map of finite type by definition of blow-up. And then you're taking a normalization of that. But since we're working with excellent schemes, right, normalization is a finite morphism. So it's a map of finite type followed by a finite morphism that's going to be a map of finite type. Next, the fiber of the closed point, that's a closed subscheme of codimension 1 in X. And that's because of the property of blow up. Whenever you blow up an ideal sheaf, it becomes locally principal, right? Which is why the fiber of the closed point is a closed subscheme of codimension 1. And why is it closed? Well, that's because the property excellence has to play a role somewhere in the proof. Okay. The next point is that now since X is normal by construction, its singular locus has to be of codimension bigger than or equal to 2, because in codimension 1, what is the stock? That's so locally that's a normal ring localized at a minimal prime. That's a DVR, right? So you cannot have any singularities in codimension 1. Okay. So, well, now this fiber, it's a closed subscheme of codimension 1, but the singularities that all live in codimension 2. So I can find a point in the fiber which is non-singular. And all the points in the fiber map to this closed point by construction, right? So this is what the fourth point says, okay? And we're going to call that point, we'll pick any point in the fiber which is non-singular. We'll call that stock at that point to be S, okay? And denote its unique maximal ideal by MS, okay? So from the construction of S, we have all these properties, right? That this regular local ring S, it dominates B, right? They have the same cool dimension. S is essentially a finite type over B because phi is a finite type morphism. They're the same field of fractions because pi is a birational map, right? And also the residue fields are the same, okay? So if we didn't assume K to be algebraically closed, this would be a finite extension of residue fields. But since we are working with algebraically closed fields, that cannot happen, right? Okay. Now, once we have constructed this S, we're now going to construct a valuation of the quotient field of S or B. And using that valuation, we're going to construct certain convex bodies, okay? So the next few lines would be about constructing a valuation which is going to dominate S. And consequently, that's going to dominate B at its homogeneous maximal ideal. Okay, now, right, so, okay, so D be the dimension of P, and since S is a regular local ring, right, we can find some D regular system of parameters. Let's call them Y1 through YD, okay? And now we will pass to the completion of S and construct a valuation there, and then we're going to restrict that valuation to S, okay? So what you do is you pick any rationally independent real numbers, lambda I, which is bigger than 1. It can be anything, okay? And then, well, by the Cohen structure theorem, right, the completion of S will have this kind of form. It's a polynomial ring. It's a formal Passer's ring over K in D variables. Okay, so any element in the completion of S can be written in this form, right, where these AIs, they're elements in the field. Okay, and then you set nu of F to be, well, you set the value of each yi to be lambda I. Therefore, the value of each monomial of y1 to the I1 rate dot 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 yd to the id would be I1 lambda 1 plus dot dot id lambda d, right? And you take the minimum over all such monomials where the coefficient is non-zero. And that's going to give you a valuation, because that's precisely due to the fact that if you have two monomials, it cannot have the same value. That's because we have chosen this lambda i's to be rationally independent. Okay, it comes from there. And one can show that this valuation nu, its value group is going to be direct sum of z, right? Z lambda 1 plus dot dot z lambda d, and its residue field, it's going to be k. Okay, in fact, it's an Avianker. It's what's called an Avianker valuation. Okay. So once we have constructed this valuation, we can construct this valuation ideals k lambda. So given any positive real number lambda, you can define k lambda to be all elements in the quotient field whose new value is bigger than or equal to lambda. And this k lambda plus is all elements in the quotient field whose new value is strictly bigger than lambda. Okay. Now, what's the need for doing all of this is because this is going to help us create those Okounkov bodies, which we'll be interested later on. Okay, so the first thing to do would be to get a short exact sequence. And for that, we need a statement of this kind. That is, you can linearly increase n, right, such that k alpha n intersection bn is going to be contained in some linear power of the maximal ideal of R times Bn, okay? And this is going to be established in 3 steps as follows. First is to show that I can find some constant rho such that k rho intersected with S is contained in the nth power of the maximal ideal of S, okay? And the way you do it is simply you can pick rho to be this value or something greater, and this is a purely combinatorial argument. Okay, which will give us this inclusion. The next inclusion, well, this shows that, well, this is ms raised to some constant times n intersected with p is going to be contained in the nth power of the homogeneous maximal ideal of p. So the point is that since S dominates B localized at MB, right? So you have, okay, let me see if I can write here. So you have this domination map. So there are 2 topologies on this local ring B localized at MB. One is the topology which comes from the powers of the maximal ideal of this local ring. And there is another topology which comes from intersecting powers of the maximal ideal of S with this local ring. And this theorem shows that those 2 topologies are linearly equivalent. Okay, and this proof, it's a difficult theorem, and its proof relies on R being analytically irreducible, meaning the completion is a domain. But since you're working with Passer's ring over a field, so that is automatically there. Okay. Third, again, a combinatorial argument is going to give us this sort of statement, right? And now if you take alpha to be the product of this rho, gamma, and c plus 1, it's going to give you precisely what you want. Okay. Right. Now, once we have this inclusion, we're going to get this short exact sequence. Okay. And just check that this is the length we were interested in initially, right? But then I can write this length as the difference of the length of the middle term and the length of the first term. So now it suffices to show that these limits will exist, right? And the point is, the way we prove the second limit exists is very similar to the proof that the first limit will exist. So we're only going to focus on the first part of the proof, right? Because the proof of the other part is very similar. So now this is where it gets interesting. We're going to construct these sets inside n tuples and in d plus 1 tuples of natural numbers as follows. Okay, I'm not going to read out what this is. Okay, so one can construct these sets gamma and gamma bar in this manner. And then one can also check that the length of, well, this was the term that appeared in the short exact sequence, right? So this is nothing but the elements, the number of elements in gamma whose d plus 1th coordinate is n, and the same holds true for gamma bar. Okay, again, these proofs are not very difficult. Okay, and these bodies, these sets are called the Newton-Akhundkov bodies. Okay, and they've got tremendous use. They've found tremendous applications in commutative algebra and algebraic geometry, especially to prove results of this kind, where you have to prove existence of certain limits. Okay. Right. Now you need some notations for convex geometry. Again, I'm not going to read them out, but the point is, we have this lemma, that is the gamma that we constructed. It has some properties, that it's a subsemi group of n d plus 1, and moreover, you have that m of gamma is 1. Well, what's m of gamma? This comes from 0.6, right? So because of my own lack of ignorance in convex geometry, I do not completely understand what these things mean. But the point is, if you just believe this statement of Kaveh and Khovansky, right? This is a generalization of a theorem of Akhundkov that says that if you have S, a semigroup S, which is strongly non-negative, again, the definition of strongly non-negative is given here. Okay, it's here. And then this limit is going to exist. Okay, now if you just plug in these values from this lemma, right, you see that m of s, right, this is 1. Of course, this lemma requires a proof, but the point is, again, the proof of this lemma is not at all difficult. It just follows from the from understanding the definitions of what strongly non-negative means and what these invariants mean. Okay, and then one can show that this limit is going to exist. Okay, so the whole point is to cast this whole algebraic problem into a convex geometry setting, and then use those results of Kaveh-Khovansky to prove that this limit exists. Okay. All right. So I guess I didn't do a very good job in presenting the last part of the proof, but I think that's okay. Okay. Now let's come to an application of this result. So we show that, well, Kwiatkowski showed that if you take R to be any analytically unramified local ring and take powers of a fixed ideal I, then this relative epsilon, then the epsilon multiplicity of an ideal exists as a limit, right? So we are able to generalize that to Noetherian graded family of ideals. And that follows from setting B to be, well, you take B to be a polynomial ring in one variable, graded by the usual way, and then you define A to be this Rie's algebra of this Noetherian graded family of ideals, right? And when one computes a relative epsilon multiplicity, this is nothing but this quantity. Okay, so we are able to extend this to Noetherian graded family. Okay. Now, of course, a natural question would be, can you extend this to a arbitrary graded family of ideals, not just Noetherian? You can even have non-Noetherian graded families. So I was kind of thinking on that. So whatever Noetherian graded families I could think of, the natural ones comes from valuations. In all such examples, the limits seem to exist. So maybe it's a direction where one can pursue to prove this thing for, or at least say something about what happens in the non-Noetherian case. Okay, so that's sort of the future plan. So if you have an excellent reduced local ring, and if you have a graded family, not just Noetherian, does this limit exist? Okay, and the next thing what one can look at is that, well, Katkoshi showed that if you have an analytically unramified local ring, then epsilon of I does exist as a limit for all ideals I and R. But what if? But the question is, can you extend that ring, as in find necessary and sufficient conditions on the ring R such that the epsilon of I is going to exist as a limit for all ideals I and R? Okay, so these are the two directions where one can go ahead with that. Okay, so yeah, I guess that's all I had for today. Thank you.
Thank you, Suprajo.
Yeah.
Are there any questions? Okay, so if there are no questions, let's thank Suprajo for a nice talk. Thank you, Suprajo.
Thank you.